Hello everybody. Welcome back to this training on natural language processing. We have indeed come a long way in this training, covering a lot of topics by now. And if you have been watching the videos and following them all through, then I'm sure by now you are quite close to becoming an expert on this topic. Today's topic will actually take you closer to that goal of becoming an expert in natural language processing so that you can handle confidently at least 70 to 80% of the use cases or business problems which involve using NLP. So today we are going to discuss about something which is called latent semantic analysis. And as the name itself suggests, uh, this is an approach which tries to tackle the semantics, which is an intrinsic part of any language. Right. So before going into the details of LSA or latent semantic analysis, let us do a very quick recap of the vector space model, which we discussed in one of our previous videos. And the reason we were doing this recap is because uh, the latent semantic analysis is actually an improvement, an extension of the vector space model that we previously discussed. So what was the vector space model doing? The vector space model was actually representing every document in a vector space of a certain dimension, and the dimension was actually determined by the size of the vocabulary. So in an example where, let's say, we are dealing with capital N number of sentences or capital N number of documents, and we have a total of small n number of terms across all those documents, unique terms, which is also called the size of the vocabulary, then each sentence is actually represented in a vector space of a dimension small n, which is the size of the vocabulary. And each sentence is actually it can be thought of as a coordinate point in a vector space of dimension small n, which is the vocabulary size. And the other way of interpreting this representation is that if you look at the document term matrix, then every row of the document term matrix is actually a representation of the corresponding document or the corresponding sentence. So every row will actually be a document vector of that particular document or that particular sentence. And since there will be a number of components in every row will be equal to the total number of unique terms that we have in the data, it makes perfect sense to say that every row is actually representing the corresponding document or the corresponding observation or the corresponding sentence in the vector space model. And this kind of representation we have seen, it also enables us to calculate the similarity between sentences using something that is called a cosine similarity. So that was a vector space model for representing text data. Now, there are certain drawbacks of the vector space model, and it's actually one of those drawbacks which will motivate us to develop something called latent semantic analysis. So let us consider two Facebook posts, right? And I'm cooking up this example out here. Don't go and search in Facebook for these posts. You may or may not get. So let's consider two posts, right? The first post says, this time of the year, people buy cars, but the high fuel prices will for sure reduce sales. And the second post says, petrol price is so high, petrol price is still so high that this will impact automobile business this season. So in a sense, both these sentences or both these posts are semantically same, right? Because they're talking about the same concept, that and the concept being that the fuel prices are very high, which will impact automobile business or sale of cars during a particular time of the year. Now, So we are all convinced that semantically or meaning wise these two sentences are pretty much the same, but then and in this case, we are looking at a vocabulary size of 16. So if you look at the words, the terms which are underlined, they are the terms of interest, and the rest are all the stop words, and there are 16 such unique words across these two sentences, so the vocabulary dimension is 16. So essentially we can represent both of these sentences in a 16 dimensional vector space, right? For the according to the vector space model. But if you see in the vector space model, the similarity or the cosine similarity between two sentences will be high, provided there is a significant amount of overlap of terms in the two sentences. So the cosine similarity in a way is directly proportional to the number of common terms that are there in the two sentences. Now, in this example that you see, these two sentences, they have only two common words, right? And these words being, I think, price is one common word, price and prices. So if we do stemming, prices will actually come down to price. And what is the what is the other common word? I think yeah, let me check out. Time is there only in the first sentence. Uh, there was another common word. I think, yeah, high. High is the second common word. So there are just two common words in these two sentences, but yet semantically they are the same. So but since the common number of common words are less, cosine similarity is not expected to be particularly high. So, so what it immediately tells us is that, in the vector space representation of sentences, and the kind of similarity measure it leads us to, one of the drawback is if the same thing is spoken in two sentences but their representative words are different, then they will not appear to be similar. And this can well happen, right? Because language is one such thing where the same thing can be expressed in many different ways using different terms altogether. So that is a glaring drawback that we have for the vector space model, and we'll see how LSA addresses that. So intuitively, what can be a solution to this problem, right? So if you see what creates the problem in these two sentences that we are talking about, the problem arises from the fact that even though the sentences are semantically same, but the words with which the meaning has been expressed are quite different. So in one of the sentences, somebody is calling fuel, in the second sentence, the person is describing that as petrol. Then automobile and car, they are pretty much the same thing, but expressed in different terms. And again, sales and business, pretty much having the same semantic meaning, but expressed in a different way. So if there is a way by which we can represent petrol and fuel not as separate dimensions in the vector space model, but as a single dimension, then it can help solve the problem, right? Because originally in the vector space model, every unique term will represent an independent dimension of the vector space model, right? So in this case, definitely fuel and petrol will be two independent dimensions. So will be sales and business, and so will be cars and automobiles. So even though these are similar terms, or in a way you can call them as synonyms, but yet in the vector space model they will be represented as independent dimensions and not as similar dimensions. So if we can, instead of representing petrol and fuel as two independent dimensions, we can represent them as a common dimension. So let's say we can combine them in some way, alpha times petrol plus beta times fuel, and call that a D1, and represent both petrol and fuel by a single dimension D1. then it solves the problem to a certain extent, right? Because then what we are saying is whether you call it petrol or whether you call it fuel, it's all the same. So kind of you are teaching your vector space model the concept of synonyms. So if that can be done, then this problem can by and large be overcome. And similarly for car and automobile, and then also for sales and business, right? So if these terms, instead of representing them as independent dimensions, if we can combine them and represent as a single dimension, it sort of helps solve the problem that these are actually synonyms or similar meaning terms. Now, apart from solving this problem, it also solves another problem. So, right through NLP problems, we have seen that dimensionality is a big issue here, right? Because the number of unique words that we see in a in any given data that we will handle will typically be very large, compared to typically the number of features that we generally handle in machine learning problems when we are dealing with non-textual data, right? So dimension is a big issue here. So this approach of combining some of the related words and representing them as a single dimension in the vector space model rather than as different dimensions, it also helps bring down the dimensionality of the problem. So if you see, if I represent petrol and fuel by a single dimension, and also the same for car and automobile and the same for sales and business, then the size of the vocabulary actually comes down from 16 to 13. So it comes down by 3 units, because I'm saying that petrol and fuel are no two separate things but the same thing, and similarly for the other two pair of words. So this approach of representing synonyms in a relational way not just helps solve a problem of semantic, but it also helps bring down the dimension, which is a good thing. So, uh, formally, if we now state that what are the two problems of the vector space model which LSA attempts to solve, they are called synonymy and polysemy. Synonymy is something which we were just looking at, right? So, two words which might be different but may have the same meaning, or may relate to the same context. So this is just very similar to the example we were looking at. So lift and elevator is another example, right? So these are kind of synonyms. So synonyms are words which are different words but they have the same meanings. The other problem, which is more subtle to tackle, is called polysemy. And polysemy actually means that it's the same word, but because it is used in two different contexts, it is having completely different meanings altogether. So just to explain it with an example, so if you read this crazy looking paragraph, and I'll read it out for you. So it might sound absolutely crazy, but then language is like this. I mean, you'll not, don't be surprised if you get this kind of sentence constructions in your data that you're dealing with. So here the sentence goes like this. A lady is actually complaining about her husband, which is not an uncommon thing, by the way. Uh, I banked on my husband. He was about to drop me to the bank. And then she says that he got late and I wanted to take a cab, but there was a taxi strike. I ended up driving my husband's vehicle. It was showing low fuel warning. I had to go to the petrol pump to refill, and by the time I reached, the car parking was full. So if you look at the words which are colored here, you'll see a pattern. So the banked and the bank. So if you do a stemming, then banked will be stemmed to bank. But this bank and the second bank here are completely different. So this bank means that the lady actually relied on her husband, and unfortunately he let her down. But the second bank actually refers to the financial institute. Similarly, if we look at the words cab and taxi here, so banked and bank, this is an example of polysemy, right? Because if we stem banked, it will become bank, but these two banks are not the same, right? So again, a river bank, if somebody talks about river bank, that can have yet another meaning. So that is another polysemy example. Again, cab and taxi, this is kind of a synonym, right? So different words, but they mean the same thing. And then I ended up driving my husband's vehicle. That is also, you can consider vehicle and car to be synonym here, uh, because these are different words having the same meaning, and so is fuel and petrol. So if you see, uh, so these are very common things that we encounter in language, right? So synonymy is still a easier problem to solve, I would say, because you can combine words having the same meaning and then represent them as a single dimension. Polysemy is slightly more challenging because polysemy will to understand polysemy, you actually have to understand the context as well, because the fact that two words which are absolutely the same but they are having completely different meanings because they are appearing in different context. So to be able to make this statement, you should be able to find out that what these different contexts are. So both these problems are challenging to tackle, and LSA is an algorithm which tackles these problems, right? So, so how does LSA tackle this problem? So we'll go into the nitty-gritties of the algorithm. So thus far, we have been looking at the construction of the LSA approach in a fairly intuitive way. And now we'll try to go a little bit more mathematical in order to try and understand what LSA actually does. So we started off with a very intuitive introduction, and then we'll do a little bit of mathematics. But don't worry, when we will wrap up with an example or an illustration, so that we wrap up on a simpler note. Okay, so polysemy. So the problems which I was referring to, polysemy and synonymy, both these problems, they actually relate a lot to context of the sentence, right? So it is the context of the sentence which will tell you a lot about synonymy and polysemy. But how do you actually determine the context of a sentence? So a very fundamental approach of determining the context is, if you find out that there are certain words which are more likely to appear together. Whenever they appear, they are more likely to appear together than some of the other words. Then you can say that these group of words which are more likely to appear together in the data, they actually determine or define some context. Similarly, there can be another different pair of words which are more likely to appear together in the data, that you can call them to be uh, another set of context, right? So identifying the context is a very fundamental thing in LSA. And in order to identify the context, along with the document term matrix, which thus far has been the building block of almost everything that we have done, along with the document term matrix, the other thing that the algorithm looks at is something that is called the term co-occurrence matrix. Now I'll explain what the term co-occurrence matrix is, but once I explain, it will be very apparent to you that it's actually derived from the document term matrix. So the document term matrix continues to be the fundamental building block, but then the TCM, or the term co-occurrence matrix, is something which adds another dimension to it. So term co-occurrence matrix, actually, it's unlike the DTM, it's a square matrix, right? And the dimension of the matrix is equivalent to the size of the vocabulary, the number of unique words that we have in the data. And it's a square symmetric matrix, because the ijth element of this matrix actually says that number of times the word I and the word J, they have occurred together in the same document. So independently, the words I and J, they may occur across different number of documents depending on uh, whichever data you are handling. But then the term co-occurrence matrix actually looks at number of times the words I and J, they have occurred together in the same document. So that is what the representation of Wij is. And you can, instead of representing this as the frequency, you can also instead of representing them as the raw frequency, you can also scale it down, or normalize it by the size of the vocabulary or the total number of words. That doesn't change the interpretation at all. But I hope it's pretty obvious that this is a symmetric matrix, right? Because I and J here are interchangeable. So words I and J co-occurring together is the same as saying words J and I co-occurring together. So why does this term co-occurrence matrix appear to be important for LSA? It is obviously so, because it tells us that which words are more likely to co-occur together, or which words are more likely to occur together than some of the other words. And it's this concept which helps us define a context. For example, in the example that we are dealing with right at the beginning, if we see that the two words fuel and petrol, they are more likely to, they have a high co-occurrence count in any data. It will immediately lead us to the conclusion that they are possibly synonyms, because they have a very high co-occurrence count, and whenever they appear together. Or even and not just synonym, they can be words which are contextually related as well without being synonyms. So let's say if we see the word car and fuel, they have a high co-occurrence count, so obviously they will not be synonyms, but then we can easily infer that these are contextually related words. And it is the identification of the synonyms and the identification of the contextually related words which help us understand that what are the hidden contexts in the data, or the latent context in the data, right? So that's about the term co-occurrence matrix. Now what LSA does is it uses the term co-occurrence matrix to try and find out that what are the hidden concepts, or what are the hidden contexts in the data, and thus tries to address the issue of synonymy and polysemy. Now the LSA approach is pretty much like this. So it assumes that in the entire data there are certain hidden number of concepts or contexts in the data. And concepts and contexts are basically, it can be a theme, it can be a particular topics, it can be something expressed about some particular domain. And these concepts are assumed to have contextually related words in them. So essentially it is a mapping between these hidden concepts and all the words uh, present in the data that you're handling. Now, if you think of this mapping, theoretically speaking, this mapping is actually a Cartesian product. So all possible combinations can be theoretically thought of to be possible. So if you assume that there are a total of n different concepts, or n different contexts hidden in your data. And what can be this context? This context can be discussion about uh, car and fuel price. It can be discussion about new car launches. And then it can be discussion about the government duties on car likewise. So if we assume that there are n different concepts hidden in the data, then theoretically every concept can be linked to every word. And assuming that there are p many words, which is the size of your vocabulary, theoretically every concept can be related to every word. But then in reality that is never the case. And had that been the case, then doing something like an LSA would have been futile, right? Because the idea here is that some of the words co-occur together more often than not, and these are actually contextually related words, and they lead to definition of the concepts. So, if given a data, all of these mappings are not very prevalent. It's only some of these mappings which are prevalent. So we will have a set of words which will be contextually related, and that will be linked to concept one, and then we can have another set of words which will be contextually related, and they will be mapped to some different concept, and so on and so forth. And this relevant mappings, or which are the words which are contextually related, and hence they can be grouped together to define a concept, that is actually determined based on the term co-occurrence matrix, and the term co-occurrence matrix, or the structure of the term co-occurrence matrix, actually depends on the data that you are handling, and which is again derived from the document term matrix. So just to carry forward this example a step further, let's say if your data is a collection of journals, published journals from two different domains, and let they be statistics and modern physics, for example, then uh, some of the terms like probability, distribution, regression, etc., they will be more likely to co-occur together compared to some other terms like atom, energy, wavelength, etc. And it would be, and obviously at the onset you will not know that statistics and modern physics, these are the two hidden concepts, right? Because concepts are latent, they are hidden. It's not known to you what are the context. But by looking at the term co-occurrence structure, you can actually find out this pattern that the terms probability, distribution, and regression are more likely to occur together in some documents, whereas the terms atom, energy, wavelength, etc., they are more likely to occur together in some other documents. And then this co-occurrence structure or contextual relationship between the words will actually lead you uh, to the conclusion, or to the fact that two of the hidden concepts in the data here are statistics and modern physics. Now, obviously, while I'm constructing this example, I am definitely not ignoring the fact that there can be really subtle intrinsic connections between statistics and modern physics. Almost every discipline is becoming, every domain is becoming interdisciplinary these days. So obviously there will be connections, but at a macro level, yeah, this example illustrates how word co-occurrence structure can be used to define different contexts in LSA. And then it helps reduce dimension as well, because once you have identified this, you will definitely not represent probability, distribution, regression, these terms as independent dimensions, but then you will combine them and represent them as one single dimension, and you will call it as statistics. Similarly for the terms related to modern physics. So that is how you get the contextual relationship of the words. You get to know what are the hidden concepts, and you also achieve dimension reduction, as we were alluding to in the beginning. Okay. So, so that is how the dimension reduction happens, right? So, if you recall the example we started off in the beginning, uh, the co-occurrence structure of the data, the word co-occurrence structure of the data will actually tell us that in this example of fuel prices and car sales, it will tell us that petrol and fuel, they generally co-occur together in a particular set of documents, and car and automobile, they co-occur together in a particular set of documents, and then they will be combined together, and then the context or the concept here will be a fuel price and its impact on car sales. So it combines a lot of dimensions together, and gives you one single context, which is one single dimension, and thus achieves dimension reduction. So we have been really looking at an intuitive approach to understand how the LSA problem is, first of all, how the problem is formulated, and then how it helps us. Now we will look at, how is the solution actually executed. And when I say solution, what I mean is, obviously the term co-occurrence matrix is there, but then how do we understand that? What are the hidden concepts? How do we find out contextually related words? And how do we actually achieve the dimension reduction? So how does that happen? So uh, in terms of execution, for LSA, as a convention, generally we work with the term document matrix, which is actually the transpose of the document term matrix. So it's absolutely the same thing, just that in the term document matrix we have the terms in the rows and the documents in the column. So it's just for the sake of representation. Otherwise, it's absolutely the same same as DTM. And like we have seen, the DTMs are very high dimensional matrices, and so will be TDM. So what LSA does is it tries to do a matrix factorization algorithm, so that the dimension can be reduced, and the algorithm used here is called a singular value decomposition. So I'll briefly touch upon how this works without going into the intricacies of the linear algebra associated here, but we'll cover this matrix factorization approach and the singular value decomposition only to that level of detail which is essential to understand how LSA works. So the first step in LSA is actually to do a matrix factorization of the term document matrix using singular value decomposition. So what is singular value decomposition as far as linear algebra is concerned, and how does it apply in this case? So let's say we start off with a term document matrix which is A, and it's of the order T cross D, T being the number of terms or the size of the vocabulary, and D being the number of documents or the number of observations that we are handling. And this matrix A, which is the TDM, is represented as a product of three matrices, of which the first one is represented as a T cross N matrix, T being again the the number of unique words or the number of tokens. S is an n cross n diagonal matrix, and D is again a D cross n matrix, where D being the number of documents or the number of observations. So what is n out here? So we already know T and D from the definition of the problem itself. So n is generally taken to be the minimum of T and D. So it is the minimum of number of terms and the number of documents. Now in most problems, the minimum of T and D will actually be D, because we'll have far too many terms than we have number of documents. So in most cases, minimum of T and D will be D, which is the number of documents, but then that is how n is set to, right? And this T and D, these are actually matrices such that if you multiply them by their transpose, the product is the identity matrix. So these are orthonormal. Okay, and uh, and what we do is we look at the matrix at the center, which is the singular, which is also called the singular value matrix, with special interest, because that actually helps us determine that how to do the dimension reduction out here. And um, and and the diagonal matrix S, it actually, the values, these are called the singular values of A, right? And also little, if you do a little bit of linear algebra out here, you will see that the number of non-zero singular values will be equal to the rank of the matrix A. So if the rank of the matrix A is R, then exactly R out of those singular values will be non-zero, rest will all be zero, right? Okay, so moving on. So this is how singular value decomposition is done. Now, instead of looking at all the singular values, if we just look at, let's say, the top k singular values with respect to their magnitude, right? Then and k can be something which we can suitably choose. Then we are able to, just by looking at this expression, we are able to bring down the number of columns of T as well as the number of columns of D, just by restricting ourselves to not all singular values, but just k of the singular values, which means looking at not all rows, all columns of the matrix S, but looking at only the k rows or the k columns, and that helps us reduce the dimensions of the number of columns of the matrix T as well as the number of columns of the matrix D. And how is K chosen? So algorithmically and mathematically speaking, K is chosen in such a way that the L2 norm of A minus X. So A is the original term document matrix and X is the term document matrix with considering only the k top singular values. So k is chosen in such a way that the L2 norm of the difference of these two matrices is minimized. Now, in more simple words, when you are actually doing LSA in real life, you don't have to bother about this L2 norm too much. So you can look at the magnitude of the singular values in the S matrix, starting from the highest to the lowest, and you can take the maybe the top 5, top 10, or the top 20 highest singular values yeah, by looking at what proportion of the total sum of the singular values they explain. So you can cumulate the singular values and then see that what percentage of the cumulative sum is represented by the first singular value, second singular value, so on and so forth. And then maybe you can take the first k singular values such that they represent 70 to 80% of the total sum of the singular values. So which is a much simpler way of doing it rather than looking at this complicated expression, but mathematically or as far as linear algebra is concerned, this is how the thing works. Okay, so we have been doing some looking at some really nasty looking expressions. So let us try and simplify things a little bit. Okay, so the matrix factorization, so how does it work? So we start off with okay, it's a typo out here, it's not the DTM, it's actually the TDM, but again, I mean, as long as you understand, it's fine. So it's the term document matrix, so term cross document, that is represented as a product of three matrices. The first matrix, we call it the term matrix, the matrix of terms. The second matrix, or the matrix in the center, that is actually the diagonal matrix of singular values, and the matrix on the right side, we call it the matrix of documents, and that is of order d cross n, right? And by zooming in, not all of the n singular values, if you look at only the top k singular values with respect to their magnitude, then we are actually stripping off some rows and some columns from this matrix S and making it significantly of lower dimension, which would mean I'm also stripping off some of the columns of T and some of the columns of D as well. So this is how it will look like, right? So if you focus on the green part out here, the green part will be the leftover part. If I look at not the not all singular values but the top k singular values, then and I take the top k's highest singular values, then the matrix of terms, it actually becomes a t cross k matrix. So the number of columns get reduced, and similarly the the matrix of documents, there also the number of columns get reduced. Remember that n, which was the original dimension of the uh, singular value of the singular value matrix, was actually the minimum of the number of terms and the number of documents that we had. And in most cases you will see the minimum of number of terms and number of documents is actually the number of documents, because we generally have far too many terms. Okay, so with this expression of the singular value decomposition, what can we achieve, right? So we will look at that based on an illustrative example. So this example is taken from, it's a very popular example to explain the concept of LSA, and this has been taken from one of the celebrated publications on LSA. So here you actually have 9 documents, right? So the first set of 5 and then another set of 4 documents. And the first 5 documents, these are basically uh, technical memos or titles from some of the research work or some of the journals, and the first 5 of them are pertaining to work in the area of computer science, human machine interaction, and the last 4, which are labeled M1 to M4, they are basically the titles from some of the technical work publications in the area of mathematical graph theory. So two quite different domains seemingly. Again, as I was saying, these days every domain is becoming interdisciplinary. So maybe human-machine interaction is also linked to graph theory. But then, for the sake of this illustration, let us assume that these are two very different domains. So C1 to C5, these are titles of some of the work done in the area of human-machine interaction, and the last 4, M1 to M4, these are titles from some of the work done in the area of mathematical graph theory, and we'll see what we extract out of this. So this was the data, and this data, from this data we can very easily construct what is called the term document matrix. So there are 12 tokens or 12 unique words, and there are 9 documents on 9 observations, C1 to C5 and then M1 to M4. And the frequencies in the term document matrix basically mean that number of time this particular term was present in any particular document. So for example, the 2 here would mean that the term system uh, is present 2 times in the document labeled C4. So if we inspect C4, we will see that system and human system engineering testing of EPS, this is the sentence. So system appears twice there. So we have constructed the term document matrix. Now let us think of the matrix which was there on the left hand side of the singular value decomposition expression. So what we were calling as the token matrix. So this is, for this particular problem, this is how the token matrix will look like, and here this is how the singular value matrix will look like. So it's a matrix of the singular values and it's diagonal, right? And how many values do we have out here? 9, right? Because we were saying that the dimension of the singular value matrix will be minimum of the 2 quantities, which being the number of documents and the number of terms. In this case we have 12 terms and 9 documents, so obviously the minimum of these two is 9, and hence we have a singular value matrix of dimension 9. Now here, by looking at the magnitude of the singular values, let's say we decide that we will consider only the first 2 singular values. There is no hard and fast rule that you have to consider the first 2. You can consider the first 3 as well, or the first 4 as well. And the guiding principle here can be, you can add up all of these singular values and you get a number, and then you see that what percentage is the first singular value contributing to the total. So similarly, what percentage is the second singular value contributing to the total, so on and so forth. And then you would like to take the first two or three singular values depending on collectively what is the total contribution of the singular values in the total. So in this case, let us say we agree to take the first two singular values. So if we are taking the first two singular values, so we are basically trimming down the singular value matrix from a dimension 9 to dimension 2, which means we have to discard all but the first two columns of the matrix that we had on the left hand side, the topic matrix. So this one is the topic matrix, right? So this is the one which you saw a little while ago. Uh, but by agreeing to work with just the top two singular values, we are actually reducing the number of columns of this matrix to 2 and discarding all the other columns, right? And similarly, mm, this is the matrix which is the matrix on the right, and it's called the document matrix. And I'll explain at the end of this illustration that why is this called the document matrix and why is the matrix on the left called the term matrix. But here also, because we are dealing with only the top two singular values, we will discard all the columns of this matrix and work with only the first two columns. So with this setup, wherein we are looking at the first two columns of the term matrix, which is the matrix on the left, and the first two columns of the document matrix, which is the matrix on the far right. And by considering the top two singular values of the singular value matrix at the center, if we reconstruct the term document matrix, how does the term document matrix look like? So this was the original term document matrix, right? Now we have done a reconstruction of the term document matrix, and for this reconstruction, what did we do? How did we achieve this? We took the original term document matrix, then applied singular value decomposition on this matrix to represent this matrix as a product of three matrices, and all those three matrices we looked at. And then we zoomed in onto the matrix of singular values, which is the matrix at the center, and we inspected the magnitude of the singular values, and then we decided that we will work with the first two singular values, right? And then working with the first two singular values actually meant that we keep only the first two columns of the matrix in the left and discard everything else. And also for the document matrix, which is the matrix at the right, we again keep the first two columns and discard everything else, because we are working with the top two singular values. And then this selection of the two singular values and two columns of the matrix at the left and the two columns at the matrix of the right, and I take a product of them, that leads me to a reconstruction of the term document matrix, and the reconstructed matrix is the one that you see at the bottom. Now, a lot of things to inspect and infer from the reconstructed matrix, and we'll go slow and we'll go one by one. Firstly, why were we calling the matrix in the right as the document matrix? Because the reason is, it is the matrix in the right which helps us trim down the dimension of the documents. Earlier, the documents were represented by all the terms present in the vocabulary, but now we will see that we'll have a far more generalized representation. Okay, and how does this? What is the other way by which this reconstruction helps? So let us see some of the examples here. So for example, let us look at a word out here, which is, let's say, survey, right? Now this word survey, if you see, or maybe this is not the right example, let us look at the word trees. So this word trees, it is nowhere present in any of the titles from the area human computer interaction. All the counts here are 0, but it is present in 3 of the 4 uh, titles from mathematical graph theory. But then for M4, which is the fourth title from graph theory, uh, the term trees is not there. So that is why the frequency is 0. But then what the reconstruction does is, if you look at the term trees, uh, even for M4, a weight is assigned. It is not 0 as it was in the original matrix. Why is the weight assigned here? Intuitively, if we try to reason out, the reason being that the algorithm has identified that the word trees is actually uh, contextually related to mathematical graph theory, and M4 is uh, actually a title from that area. Hence, tree must not have 0 weight for M4. It should have some positive weight, right? Similarly, if we pick up an example from the human computer interaction side, if you see the word, let's say user, right? The word user, it is present in 3 of the 5 sentences that we have seen from this domain. It is not present in C1 and C4, and that's the reason why in the term document matrix, the initial matrix, the values are 0, right? But then if you look at the reconstructed matrix, the the values for user against C1 and uh, C4 are not 0, but there are some positive values, right? So once again, the algorithm identifies that the word user, even though it is not present in the documents C1 and C4, but generally speaking, the word user is contextually related to the domain human computer interaction, and C1 and C4 are actually documents from that domain, hence there should be some positive weight. So what it does is, it helps me do the following. It helps me uh, it helps me in the sense that identifying a particular domain or a particular context from a document doesn't or not a document, actually identifying a particular context from a data doesn't merely depend on few chosen words. It in fact depends on all the words which are contextually related to that concept. So in this case, if I am talking about human computer interaction as a concept, then identifying that as a concept from the data should not depend on the presence of few keywords, but it will depend on all the words which are contextually related to this domain. That is what ELISA does. So it and why does it does so? Because you see, when you are talking about a domain, and if you represent that domain by only a few fixed set of words, that is not sufficient, right? Because different people might use different forms of expression when they speak about the same domain. So essentially, your algorithm or your text representation should not rely on only a fixed set of words as a representative for certain domain. So it should generalize across a wide class of words, and that is what LSA helps us achieve. Another very interesting structure, if you look at here, in this example, the first 5 documents are pertaining to one particular domain, and the last 4 are pertaining to another particular domain. And if you see the words here, uh, starting from human till the word time, these words are more likely to occur in the context of human computer interaction, whereas the remaining words starting from survey to minus, they are more likely to occur in the context of graph theory. So if you look at the reconstructed matrix here, you will see that if you look at this the part which is highlighted out here, you will see that the words which are more likely to occur in the context of human computer interaction, they have a significantly higher weight, right? So if you look at the document C1 or the C2 or the C3, C4, C5 here, these words which are contextually related to the domain of human computer interaction, these words have significantly higher weights for C1, C2, C3, C4, C5, whereas the other words, they have significantly lower weights for C1, C2, C3, C4, C5. But then these words which have lower weights for C1 to C5, they again have significantly higher weights when it comes to the documents from graph theory. And the first set of words which were contextually more related to human computer interaction, they have significantly lower weights in the document vectors for M1 to M4. So uh, identification of the context is also aided, by this kind of a representation of the document vectors of the different documents out here, right? And this kind of representation can also be looked at, at a term level. So if you look at the terms, right, instead of looking at the documents and considering these columns as the document vectors, if you look at the terms, and let's say for a moment, if you assume that these rows are representative values of these terms or tokens, you will see that the terms which are more likely to occur in the human computer interaction domain, their weights are much higher in that domain corresponding to in the other domain. It's fairly intuitive because it kind of comes from the very construction of the document term matrix or the term document matrix. But then what the algorithm does is it does a generalization. So as I was saying, so let's say the word user, it is not there in C1 and C4, but it is there in C2, C3 and C5. But in the generalized representation of user, what it does is the algorithm gives some weight to the term user in C1 as well as in C5, and definitely in C2, C3, C4. And then as far as the other documents are concerned, which are from a different domain, the term user has very low weight. So that is also another way of inspecting the LSA reconstruction. Okay, so what did we look at? So if we summarize, we started off by saying that the vector space model has got some drawbacks when it comes to understanding synonyms and also the problem of polysemy. So words which have similar meanings but they are different words, uh, they cannot be very easily identified from the vector space model, and also same words having different meanings because of different context, they also cannot be identified from the vector space model. And we then formulated the problem of LSA, saying that it will deal with this problem of polysemy and synonymy, and in a way it will also reduce the dimension of the data that we are dealing with. And then we looked at the mathematical formulation of latent semantic analysis. We looked at some really nasty looking linear algebra expressions. You can actually, if you want, you can do some more research on it. There's a lot of literature available if you want to do a really mathematical development of LSA. That is also possible, but beyond the scope of what we are discussing out here. And then we sort of looked at how we can do the SVD, the singular value decomposition of the term document matrix, and then interpreted the three matrix products. And we looked at how we can look at the matrix of singular values and then decide to work with not all the singular values but the top k singular values, and then how the selection of the top k singular values also reduces the dimension of the other two matrices in the SVD. And then using this reduced dimension, we can reconstruct the document term matrix, and the deconstructed document term matrix will have some very interesting features, and that is what we looked at by looking at this example as well. Now, one parting note I would leave you with is it's not guaranteed that if you do LSA with any choice of the number of singular values, you will get this kind of a nice interpretation. So it actually depends on the right choice of the number of singular values or the right choice of the dimension you want to work with. So in a way it is iterative. So you have to run a few iterations, for each of the iterations get the reconstructed matrix and do some visualizations and find out that whether intuitively whether you are getting the separation with respect to the different context which is there in your data. And as always, domain knowledge also helps out here. So some of the intuitions will come from your domain knowledge as well. Your domain knowledge should tell you that what can be the hidden contexts in this in the data that you are dealing with, right? So that kind of brings us to the end of the discussion on latent semantic analysis. Like for the other concepts we discussed, we will do some hands-on as well in one of the subsequent videos. But before ending, a note of acknowledgement, heartfelt acknowledgement, because for this video I have drawn some reference, be it on the concept side or on the example side, from a very celebrated paper on LSA, which is attributed to these three gentlemen, and it is a paper which came out in 1998, and it's called Introduction to Latent Semantic Analysis. So if you want to read more, understand more of the mathematical formulation, then I really would encourage you to go through this paper. Otherwise, if you really want to have a working knowledge of LSA, whatever we discussed in the last 1 hour should be sufficient for you to apply LSA for any real life problem that you will be working on. And obviously we will do a hands-on implementation using R. So thank you for watching, and we'll be back with the next video soon. Have a good day. Bye.